Hey everyone, this is Third Derivative. I don't think I'm good at introductions, but whatever. This is Class 6. There you go. The the whole idea of Class 6, which I think confused me the most out of all people, is how to get from like oil well, like data, which was really messy, to a visualization at the end that looks amazing. Um, we can show that later. But the initial idea was to just simply collect data, wrangle it, and then find a way to visualize data. So, as Professor Joe has mentioned, the idea is to get like I would so call it noisy data from PDF that are just broken files into OCR into readable stuff. And you will see this is how we approach the problem. We just mentioned like it's really just like similar to previous previous labs. Not interesting. Something that we added along the way, we ended up using Rolling Edge to get extra like data such as world status, world type, closest city. This is this is something we wanted to use later, but we ended up having the longitude and latitude and it didn't matter. And then barrel support and gas support. Um, this in particular was especially interesting because we wanted to see if we could use this for visualization, which again will be shown later. Um, and then it's just like, this is not exactly what we used it last week for. We ended up having to get leaflet for condensing. I believe it was condensing like data points as you zoom out, and then it's just run and map and all the commentary. Everything here is probably going to show in the presentation. That's really not a lot to talk about. Um, I think a couple of things I should note during the whole process, though. First of all, um, we couldn't see like the three forms that were included. Like we only had forms 4, 8, and 19, and that's why our specific solution was to regex like between these three forms. This is this is fine for current uses and purposes. Um, this would not apply to new data sets, however, and this is something we have. However, we can say that with high confidence that our reject was really well given, like this, that we believe it can expand similar data. Um, Secondly, scanner issue. So I believe I don't remember when exactly, Tanya, if you can remember, when the files were scanned. I think it was a while.
Wait, can you, Steve? I just want to
Uh,
say, can you like speak up a
yeah,
little
yeah, yeah.
bit?
Oh, sorry. I was saying like the files were scanned quite like a while ago. Like they weren't as crisp. And this is something that most of us saw when we did like and Nerali, of course. Like all three of us saw when we did like OCR to begin with, right? There were a lot of like
Mhm.
minor mistakes.
Yeah,
Um,
the files, they were like scanned PDFs, so OCR wasn't able to pick up everything that we hoped that it would. So when we did analyze these documents with regex, a lot of the regex patterns didn't work for every single OCR output, which is what we'll get into later when we go through the code. Um, but that is something that we should probably refine again and like work on more in the future.
um, like I said, a lot of I think the first half of this just ended up being how we did OCR in lab 2 and lab 5, I believe. We did reuse it for lab 4, but so that's not a lot interesting in the first half. And the second half is going to be more fun if you actually see the work. So there's that. This time around the documentation is not that interesting. Sorry. That is it. So I think it's much better to show the visualization and then we can explain from there. So I'll leave it to you, Tanya, for that.
Okay. I'm going to go ahead and share my screen. Give me a moment. Okay. I will be displaying the code in VS Code just to have it easier to look at. Um, One of the first files you will see in the repo is something called PDF extract. Um, Basically, this is the main scraper code that we had going to go through the PDFs. And so it connects to MySQL, it creates the tables if they don't already exist. It stores the key pieces of information that they ask for in our lab instructions. Um, it also has code to convert the township and range to latitude longitude, but we didn't end up using this because it just didn't work. Um, Basically, it uses PyTesseract and Fizz to parse the PDF. Um, this is the part where we do OCR. What we try to do is detect the form type because what I noticed when working through this is that each form has a different setup for where they put things like the well name and the API number and things like that. So one way to try and make this a little bit more efficient was if we could figure out the form type, we can use those patterns in the form to figure out the information. Um, so basically there are branches in the code. There's a branch for Form 19, a branch for Form 4, and a branch for Form 8. Some of these PDFs also had multiple forms in them. So this code just basically takes the first available form and analyzes that.
Oh
Um,
yeah, it's sorry, one thing to scroll up. This is something we had to adapt. A lot of them just ended up having like operators that LLC like those that you can see, and if you go up, you will see like for I believe 19, yeah, that one. You see a lot of operator names and like whatnot. This is something we could really find a workaround. Like it's definitely easier for us to do this, but like I said, it won't generalize that well. So something to
mhm.
note. You,
Yeah.
yeah, sorry. You can,
Yeah. You want to say anything else? No, okay. But yeah, this is something we should refine in the future because obviously, if we were to get more PDFs with more wells from other locations, they won't just have these well names in them. And it's probably not smart to sit and hard code every well name we're expecting into the code. Um, there was also like a fallback where if for some reason the form type just couldn't be figured out, the algorithm would try and just use generic patterns to figure out the latitude, longitude. Um, it would print the results out for each PDF that we scan just so we can monitor what's going on. Um, and then we would edit the main loop to parse the PDFs, which hadn't been parsed yet, and it would save everything into the database. I ended up using the Google Gemini LLM with the free credits. So this little piece of script, which was the LLM Finder, helped me figure out which models we could and couldn't use for analyzing the OCR data. And then what I ended up doing was using this script to feed the OCR data into Google Gemini. And then it basically checked if whatever we had in that database was valid and made sense. If it didn't, it would go through the OCR text once again and fill in the database with the pieces of information which were relevant and which did make sense. This just helped with data pre-processing and making sure that we were ready for that next step, which would be to work on the front end. Because obviously, if we didn't have the right addresses and we didn't have the right latitude, longitude, and things like that, um, we just couldn't build the map. So that's what that is. This code is the web scraper for scraping that drilling edge website. Um, Once again, it connects to our database. It adds in the information from the HTML, and this is powered by Beautiful Soup. Um, it searches for the piece of information that the professor asked us for, which was like barrels of oil, the gas, as well as the chemical information and things like that. Um, or sorry, this also got the well status, well type, and the closest city. Chemical information came from the PDFs. Um, so once again, it scraped everything, added it to the database, and then one thing I kind of realized was that the addresses that we pulled from the website weren't always correct and accurate, or sometimes the web scraper wouldn't always pull the correct um, latitude longitude values. So what I did was I took the database, gave it to Google Gemini, and I said, hey, if the latitude and longitude aren't there, but you have the address, can you use this prompt that we came up with to um, basically give us the latitude, longitude, and plug it into the database for us. So that's
Oh
a
no, on this. Sorry. We did consider using the Google Maps API. It it was a bit too tricky. No, it would.
Yeah, maybe in the future, if we were to fix this lab up, we could use a Google Maps API instead. Just using the Google Gemini API was the easiest fix at the moment and the least time-consuming option at the time. Um, but one other thing that we also kind of ran into were API requests, and so it had to make a few, um, what's it called? Like it had to wait a little bit after each request if at first it didn't work because we didn't want to overload the API. And then again, if it did make any updates, it would let us know, and then it would update that database. And then finally, this brings us to the front end, which was powered by Flask. I chose Flask because I've worked with it in the past before for another mapping project, and this was just what I was most familiar with. Um, in the future, we should probably try and use the Apache web server and things like that. But basically, this plugs to our database. It has a bunch of helper functions to fetch the well data and the stimulation data. And it connects to map.html, which is our front end. And this is where we have the map functionalities and the stylistic choices made with CSS. This is also where we implement some of the cool features in our web app, like the search bar and the logo and things like that. And this is pretty long, so I won't get into the nuts and bolts, but what I can show you is a quick demo of our web app, which is here. We called it Site Scout, and this is the landing page. You can enter the application like this, and you're brought to a view of the contiguous 48 states of the United States. As you can see, the clusters are representing the wells in these states. You can click on a cluster, it opens out, and it shows you the wells that are there at that location. We did some color coding, so if it's grayed out, that means it's inactive. We also made the assumption that if we couldn't get some of the information, it's probably inactive. Um, in the future, we should double check and confirm this before we um, make the status like that. But if the well is blue, it's considered active. And this is the data that we were able to pull from both the PDFs and from the website. What's cool is that some of the cities you click here, it zooms in to a nicer view. You can click again, it zooms in again, and then it shows you the clusters of the active wells. Another cool thing to note is that if all of the wells in the cluster are active, the dot is green. If there are any inactive wells in the cluster, the dot is color coded to like a yellowish color. If you're done looking at the view, you can reset the view back to the US. And this kind of works in a similar fashion for the other cities as well. So it's fun to just play around and take a look at where the different wells are like that. One other cool feature too is that if you want to search for a specific well, we have a search bar function here which opens out. You can search by API, by the name or the city. So for example, if we want to look for the Atlanta named wells, you can type in Atlanta and it pops up here and you can scroll. If you want to look at a specific well, you can click on it. It actually brings you to the pop-up right here. If you want, you can actually search again. You can look at the Chalmers well. There you go. So it's like this. So if you're done looking at the views, you can again reset back to the US. And yeah, this is our web app. I'm going to pass the floor to Nirali to finish us out.
Yep, so this is amazing visualization that we got through. Like we could just see all the clusters of wells which are active and inactive. And I think what was really interesting about this whole project was how huge the PDFs were for each individual well and how much relevant information was present in each of these PDFs. And it was so most of it was irrelevant information which we had to discard. And that just made us understand the importance of data cleaning in the workflow of a data scientist. Also, from this project, I think we really appreciate why we have used this data of the wells because I think even Dr. Cho had mentioned in his class that there's something called the orphan wells where some owners like forget about the wells that they're no longer using and some harmful gases like methane and other um, harmful gases that could affect the environment and the ozone layer are emitted from those orphan wells. So to know where are they located so that we could help remove them, I think this project really helps us understand that as well. Yeah.
Yeah, thank you so much and bye.
Yeah, thank you. Bye. Yay.